Good morning. Still morning. So I like to see a high average on the first test, because that means everybody's getting the basics. And so I'm happy about this. We had an average of 83. The median was even higher. So overall, good job. It was, in my opinion, a very straightforward test. So if you didn't do as well as you would have liked to do, there's still time to recover, but you need to work on 6 down, because we're going to keep building on them. So if you didn't do well, do come and see me, and or go see James during his office hours. It's still possible to make this all work, but it will take some serious attention to a few things to catch up. The one thing that I think you weren't as good on as, so calculating things, everybody was fine. The one thing that you aren't as good as you are going to need to be eventually on is reasoning from the momentum principle. And in particular, this problem where we had 2 asteroids moving away from each other. There are various ways that you could go wrong. And I think that one of the messages is, in this course, you have to start every problem from the beginning. You can't just say, I have seen a problem like this before, and I remember the solution, and it looked like this, so I'm going to do that. Because key features are different. And so the problem we had on a quiz was electric forces, which can be repulsive, but asteroids aren't charged. Most ordinary objects are not charged. If they were, some really strange things would happen, since electric forces are so large. If you all had a significant electric charge, you'd actually be repelling each other and plastered against the walls of the classroom, or all huddled up in one bunch, depending on your... So therefore, if things are moving away from each other, they're being pulled back together, and therefore their momentum is decreasing. They're slowing down. Okay? So that's something that should be reflected when you draw a diagram of this kind. Second, so first of all, the forces have to be attractive, so no forces going off there. Second, momentum has to be decreasing, because they're being pulled back together. And third, direction of the forces, you really have to be careful. So at T1, the objects are here, and so let me actually draw them a little farther apart so I can make the arrows bigger. So the force, when they're here, they attract each other with equal and opposite forces. And now there's a question of, how do you draw a momentum tangent to a curve? Okay, so I think most of you are drawing a tangent. Okay, so we got some momenta that we're doing strange things. So basically the issue is, momentum is in the same direction as velocity. And if you think about velocity, this asteroid's here, and you know in a very short time it's going to be there, and that gives you the direction of its velocity if you pick 2 points that are really close together. So if you just draw a straight line through those 2 points, you can get something that's essentially a tangent, okay? And as these things get farther away, No, the forces don't just point up or down. They point toward where the thing is now. So basically, you need some kind of a line. A shorter yard-meter stick would work better. And the forces, they're farther away, so the forces should be smaller. And we've got momentum that's decreased in magnitude because they're being pulled back together, okay? So your momentum vector, where's it going? Right now it's going this way, and it should be significantly smaller than that one, etc. Okay, so there's an awful lot of physics without a single number. And that's part of reasoning about physics. Sometimes you do a lot of reasoning without calculating anything, but it's still very important to be able to do this. So think about these things, look over your test, the solutions are posted. If you have questions, come and talk to one of us. And we can talk about how you might improve if that's necessary. Overall, very good job. I think we can safely go on to more complicated things, which we're starting to do this week. So questions about this? Okay. Last week in lab, you did something kind of macho, actually. You did your first real computational model, you know, of interacting systems moving. You had 3 interacting objects, even though we fixed the Earth and the Moon to make this a simpler problem. And you had to calculate, you had to model the voyage of a spacecraft starting just above the Earth, traveling to the Moon, crashing on the Moon, but make the number of close-up pictures it could take as big as you could. And so this was a big model you had to put together, and a sense of accomplishment that you were able to do this. Now, from what I saw in the labs, many of you would have benefited by making a plan first instead of just starting to type code. It's solving problems on a computer is just like solving problems on paper. You need to know where you're going. And if you start, so I saw people typing code that didn't make any sense to calculate a gravitational force when I know you know how to calculate a gravitational force because you just did it on the test, and you'd also just done it in the previous little section of the trinket. So I think you just got a little overwhelmed. And so what I'd like to see when we do future models like this is a little more of a plan. And a plan can take a lot of forms, but it could be something like this. You can say, while craft hasn't reached the moon, because of course a story and words are fine, what do we need to do? Well, we're going to do this whole position and momentum update thing, but what's involved in that? Well, the first thing is we need the force by the Earth, because that's a big deal. It's slowing the spacecraft down, right? And to do that, we actually need the distance to the Earth. Now, why does this have to be inside the loop? I saw a lot of you struggling with what it went inside the loop. It's because the distance to the Earth changes. every time you take a little step. And so anything that changes has to be recalculated in the loop. In order to recalculate the force, we have to recalculate the distance, okay? So that's the kind of thing you want to think about when you're doing this sort of thing. Now we're not done, because the moon is exerting a force, so we have to calculate the force on the moon, and that means we need to recalculate the distance from the spacecraft to the moon. And now we need the net force, which is just the sum of all the forces acting on it. And now we're all set to do the thing we know how to do really well, which is update momentum and then update position. So we update. And you want to remind yourself how to do this in a program, which is a little bit different than on odd-looking P equals P plus delta T. And then we want to update the position of the spacecraft, and then we go back up here and say, has it reached the moon yet? And okay, so I think if I found something like this on a piece of paper, that would be a guide for what goes in your model, and it would make your life a lot easier. I think you think that you should just be able to sit down there and type code. And no, not at this stage, and maybe not ever, really. I mean, and we do more real-worldy kinds of things, we really have to have a plan like this to follow and to check to make sure we've done it right. So I recommend that, but you got through it, and you got it to work, and I think you should feel a sense of real accomplishment, because this is you're basically doing what NASA does to send spacecraft out to planets or moons, and you're doing this in first-year physics. And so, awesome. Well done. Good job.
Is this rocket science?
This actually is rocket science. So you're doing rocket science. So let's see. It's not where I want to be. Here's where I want to be. All right. So up to now, we've done a lot of calculating a force and then predicting where something, how that's going to change an object's momentum, and therefore how it's going to change its position. So we're predicting into the future. But there's another way we can reason about things, and it has to do with observing the motion of an object and then deducing what forces are acting on it. So being a detective, CSI or Sherlock Holmes, okay? And so what we're going to talk about in this chapter is figuring out what forces are acting on objects whose motion we know, whose motion we observe. And so that includes a velocity of 0. So and there's sort of two phases to this. One is if objects, the trivial case when objects are not moving at all, so their momentum is 0 and it's remaining 0. And then the next is a much more interesting case when they're moving, but they're moving in curves and interesting patterns and reasoning about that. So today we're mostly going to talk about the first case. And so if you're an engineer, which most of you aren't, but if you're an engineer, these two fields are called statics, standing still, dynamics, moving, and you take an entire semester course on each one. Now we're not engineers, and we're not going to do that, but what we're interested in is how we can use the momentum principle to reason about forces in motion. And so we'll be applying it to situations like this in order to figure this out. We're going to rewrite the momentum principle yet again. And this time we're going to take an instantaneous view. So you've known that we were edging up to this all along, right? So if we have delta P is F net delta T, then we can rearrange that to be delta P over delta T is F net, and we've always had this disclaimer, for a delta T sufficiently small that F net isn't changing. Well, if F net is changing fast, then in fact what we want to do is take the limit as delta T goes to 0 of this, and so we get the rate of change of momentum, the instantaneous, so this is the instantaneous version of the momentum principle. The rate of change of momentum is equal to the net force acting on. Now, equal signs are interesting in physics, and this equal sign doesn't mean they're the same thing. So momentum is, you know what momentum is? Gamma mv. It involves mass and velocity, and force is something pushing or pulling on something, so they're not the same thing. This is more like a causal relationship. So a net force causes a change in momentum. So this equal sign is really a sign of causality here. Now, what is a derivative? What does this mean, a derivative of a vector? Well, we've been working with derivatives of a vector because velocity is a derivative of position. And so we can write this, if we write it as a vector, we can write, ouch. This is the x component of this vector is just dpx dt. The y component is dpy dt. The z component is dpz dt. And that's equal to the vector that's the x component of the force, the y component of the force, and the z component of the force. So again, we've got these, this is really a very compact way of writing three equations where we have dpx dt equals f net x, dpy dt equals f net y, and I suppose I should be a little more careful and put net here. So this is the form of the momentum principle that we'll be working with this week. And I don't think it's a big surprise to any of you, actually. So today we're going to talk mostly about applying the equations that are, quote, static, which means in our terms that the momentum of the system we're interested in is not changing. Now, there are actually two ways that can happen, right? Either it can be 0, which is a legitimate momentum, or else it could be non-zero but constant. So something's traveling at a constant speed in a straight line. And in either case, the rate of change of momentum is 0. And so we can model each of these systems, each of these situations in exactly the same way. We're going to, so what we're going to do is, and so this is a case of known motion. If we know the momentum of the system is not changing, then we know that the net force has to be 0. And therefore, if we know excuse me, some of the contributions to the net force, but not all of them. We can figure out the unknown ones because the forces have to add up to 0. So that sounds kind of trivial. The interesting, and it can get arbitrarily complicated with lots of forces acting at various angles and whatnot. The interesting thing about this, and one of the reasons we're going to do it, is that it allows us to focus on something that's really very important in our problem solving in physics, which is choosing a system and then sticking with the system we've chosen and very systematically identifying all the forces acting on it. Okay. So we have some rules for identifying forces. So one is choose a system and stick to it. Don't switch. So if we have 2 blocks and 6 springs and the earth and some other stuff, we pick one object as the system, and then that is going to be the system. And everything else is the surroundings. And we have to be consistent in our analysis. Now, any choice of system is totally legitimate because the momentum principle applies to any choice of system. That useful in getting to the unknown we want to get to, so there's a little thinking involved in choosing an appropriate system, and occasionally we'll just make the wrong choice, and then we'll have to go back and try a different choice. So the next step is identify every object in the surroundings that interacts with the system. And we're going to be very compulsive about identifying, naming objects in a system. There can be 2 ways things interact. It can interact at a distance, like the gravitational, the electric interaction, which occur without things touching each other, or it occur through contact. 2 things actually touch each other. And so everything that either interacts at a distance or touches the system and once we've identified all those, we're going to stop because that's all the forces there are. And then we're going to draw what's called a free diagram that shows our system and all the forces we've identified on it. And the reason we're going to do this is that this is a big piece of our analysis. We want to record it in a compact way so that we don't have to keep thinking, wait, what were all those things I identified? And so we're going to do an object of this in a minute, an example of this in a minute. So how to make a free body diagram. If we're modeling a system as a point particle, just okay, we don't care if it's round or square or spaceship shaped or whatever. Represent each force by an arrow. And its tail on the system. And label each force. Okay, doesn't sound very hard. It's not. We just have to be systematic. So let's practice a little bit. So here's a situation we'll analyze that involves a block that's attached to two strings. One's attached to the ceiling, and you're pulling on the other with your hand. Okay? And we want to find, the ultimate goal is going to be able to find the tension forces exerted by the strings on the block, which we don't know. And a lot of these problems are designed so that you have to, there's an angle that's given, and so we're going to have to use direction cosines to get components of things. Okay? So this is our situation. We're going to choose the block as the system.
That's the blind, I think it's the location.
Yeah, I wonder if we could just raise the blind slightly to get it to stop doing that. Let's see if we can do that. Oh, the window's open. That's not really all that great. Okay, that's not a help with the air conditioning. So we're going to choose the block as the system. So here's our first task. We're going to identify objects in the surroundings that exert significant forces on the red block. So we have several choices. The earth, string 1 and string 2. There's also the hand. There's also the ceiling. Okay, think about it for a minute. Talk to the person next to you, because you all need to wake up, and decide which of those lists of objects is the one that agrees with our rules here. All right? What do you think? I'm impressed. Almost all ones. So 1 is the correct answer. And so why is the hand not an object that's interacting with our system?
Because the hand isn't actually affecting the block directly.
It's not touching the block. Now it's important, isn't it? Because if you weren't pulling on that string, then the block wouldn't be pulled over. But it's actually the string that's touching the block, the string that's exerting a force on the block. Now if we wanted to take the string as the system, then we would count the hand as being in the surroundings in the block. But in fact, and for the same reason that the hand is not exerting a force directly on our ceiling, the ceiling isn't either. Okay, so our surroundings are the earth, string 1 and string 2. And we're very careful about this because it helps us avoid double counting forces. So if we use the hand also, then we'd end up with, and it's sort of like saying the earth and gravity. Okay, well, if we name the Earth as the object, then we only count that once. We know it's a gravitational force, okay? So this is why we're naming objects. Okay, so we're going to draw a force diagram for this. And so here's what we've got. Here's the force by the Earth. It's called F2 in this diagram. That's fine. We could call it's a tension force because it's a string, right? So we could call it FT2 or something. So, but we left out string 1. So what should we draw for the force exerted by string 1 in our diagram? Okay, so what direction should we draw the force to string 2? Okay,
String 1.
I'm sorry, string 1. String 1. String 1. Does that change your answer?
Yeah.
Okay. All right, so 8 is correct. We draw it this way. And the reason we do is that it's a string. A string is kind of like a noodle, right? It's sort of floppy. And so the only way it can exert a force is if you stretch it and then the tension is along the length of the string. So a wire or a string, the force always points along that string or that wire. It can't, if you tried to push on the string, it would just collapse if you tried. So it can only exert a force along its length. Okay. So now let's see how we would solve this problem. So let's say the mass of the block is 2 kilograms and the angle theta given there is, what did I pick here? 20 degrees. And what we want to find is the magnitude of F1 and the magnitude of F2. So this angle okay. So how do we start? We start with the momentum principle. So the rate of change of this system, momentum of this system is 0. And often in these, it's maybe easier in this case, even though what we have are vector relationships. So we have the fact that dp dt equals 0 that tells us that F net is also 0, and that's equal to F net is equal to the gravitational force plus F1 plus F2, and it's equal to 0. And we could write them all out as vectors, but it's actually usually kind of convenient to just work with x and y components of these equations separately. Because we know that if dp dt is 0, then dpx dt is 0, and dpy dt is also 0. And so we can just worry about x and y separately. Now, actually, at it, it may seem a little odd that we think we can get both of these forces because there are two unknown forces and only one known force, and so it seems like there are too many unknowns. But there's a lot of information in angles, it turns out, and so this actually works out okay. So let's actually write some equations for components. So dpx dt is 0, and that's equal to what? Well, it's the x component of f2, which is, now we have to be careful about signs. Oh, that's another thing you did on the test, some of you. If you're not using vectors, if you're going to work with components, you have to be incredibly careful about signs. So a lot of people didn't think about L hat when they were talking about a spring force, got the direction of the spring force wrong. Some people even got the direction of the gravitational force wrong because you weren't thinking about signs. So you have to be extremely careful. So this is going to be a positive number. And now we have the, what's this going to be equal to? What else has an x component? So it's this force has both an x and a y component, right? So F1x. And this one is going to be in the negative x direction, and that one's in the positive x direction. What about, and is that it? Are we done with x? We're done with x. dpy dt equals 0, and that's equal to the y component of the gravitational force, which is negative, plus the y component of this F1, which is going to be a positive. Okay, well now we're getting somewhere because we can calculate the gravitational force, right? So that part's good, that's easy. So let's do that. So we have gravitational force, the y component is minus m times g. And we know that, so we can actually rewrite this equation as 0 equals a minus m times g plus the magnitude of F1 times what? How do we get the y component of F1?
The square root.
Well, if we knew the vector, we could take the square root of the sum of the squares, but since we don't, what does this angle tell us here? Okay, so remember that we can write F1 is equal to the magnitude of F1 times the vector cosine theta x, cosine theta y, cosine theta z. So F1y is equal to the magnitude of F1 times cosine of theta y, right? And we know that angle because this is the angle between this and the y-axis. So we end up with minus 2 kilograms times 9.8 newtons per kilogram plus F1 times cosine of, what is it, 20 degrees? And here I'm writing without any decorations as meaning the magnitude of F1. And so we can actually solve for the magnitude of F1. That's equal to a minus mg over cosine of theta y here, right? Oh, plus. So, plus. Plus, are we happy? Okay, and we could plug numbers in that and get a number for F1, right? So, well, now we know that. Now we can go back. So we've got that. It's given us the magnitude of F1. Now, can we use that to get the x component of F1? How do we get the x component of F1? The x component is the magnitude of F1 times cosine of theta x. And what is theta x in this case? And what's the angle between F1 and the positive x-axis? Okay, so this is theta y. What's theta x? It's that angle, isn't it? So it's 90 plus 20 degrees. So we have, this is equal to the magnitude of F1 cosine of 110 degrees, if I can add, which is sometimes so now we know this. We can solve for the x component of F2, right? So, and this is going to be a negative number because cosine of 110 is going to be negative. So now we're going to get F2x is a minus F1x, which is a minus F1 cosine of 110. And how does the x component of F2 relate to its magnitude? It is the magnitude, isn't it? Because that's the only non-zero component in F2. So this gives us F2. So, and we could plug numbers into that and get numbers. But so questions about the reasoning we went through. In a certain important sense, when you've got this diagram, you pretty much have the solution. You have to translate it into these component equations. And then you just start grinding through. What you do at that point is say, well, what do I actually know? And you find that you typically know the gravitational force on something, and therefore you could solve for this, and that helps you solve for that. Okay, so it's just a chain of, so basically you have two equations and two unknowns, which works. We did it by substitution. You could so questions about that? So we did need to be very systematic in identifying forces, and we had to be careful not to include the hand in the ceiling. And we had to be careful not to forget the earth. Okay, but once we did all that, you sort of grind through the solution. Okay, so let's think about another situation where we can maybe apply this. Okay, so we have a 10-kilogram box. We are pulling it across the floor with some force acting at some angle of, what, 25 degrees. And we know that the coefficient of kinetic friction is 0.5 for this system. This box is traveling at constant speed, so it's traveling at well, it's only 10 kilograms. It's traveling at 0.7 meters per second. And we want to find out how big a force you're exerting to pull it. Okay? So what I want you to try to do, take a minute and draw the free body diagram. Choose the box as the system. And let's draw the free body diagram for as the system, which means you have to identify all the objects in the surroundings that it's interacting with. And you have to use arrows to represent them in the diagram. And if you do that really, really quickly, you might try writing equations. Okay, so what do I do for the free body diagram here? Here's my box. That's my system. So what are the objects in the surroundings that are exerting a force? The Earth. So we have what else? Yeah, the table or the floor, right? So, okay, that's an interesting one. What's the direction of the force exerted by the Well, there's okay. So this is an interesting interaction. So remember what we did last week. So what's going on? Why does it matter that the table's there? There's friction, okay? So if you want, we can say one of the things the table does is exert a friction force, which in this case is opposite to motion. Now, friction forces actually aren't always opposite to motion. For example, suppose that you have a conveyor belt traveling along and you drop your suitcase on it. Okay, well, there might be a little slippage at first, but what happens? The suitcase speeds up until it's traveling in the direction of the conveyor belt. So what force made it speed up till it was traveling with the conveyor belt? That's friction, so it was in the direction of motion. So you have to be a little careful about that, but in this case, yes. Is that the only thing the table's doing? What else is it doing? There's a force perpendicular to the surface, isn't there? So it's actually, we've got this. So what we've really done is, so really what the table is only one thing, so really what the table's doing is exerting a force that has a negative x component and a positive y component, and it's depending on something like that. It's probably like that. It does in fact make sense for our analysis to think of it as the sum of two different forces by the table. One that's just opposing the gravitational force because we compress the interatomic springs in the table, and the other that's friction, that's making it hard to pull the box. And what's the final thing I need to add? So okay, and I'm pulling at an angle, right? So how do I draw that? So I just draw so I think we just called it F here. Okay, so this is the key piece of the analysis. Almost all the physics just got done right here. Okay, we picked a system, we stuck to it, we counted forces. Okay, now let's just try to write out the equations, the x and y equations we'd use to solve this. So take a second. Remember, we want so what is dpx dt? What's the value of it here? Everybody. Zero, right? Because the velocity is not changing. And dpy dt is also zero because it's not changing up and down. Okay, so see if you can just write out those equations. We don't have to solve them, but Okay, I see some equations. So basically we're just going to kind of read these equations off the free body diagram, right? So let's start with x. So it makes life a little simpler if we talk about magnitudes in our equations, because then we can write pluses and minuses. So what goes here? What's one of the things that goes in the x? So friction. So here's F, and if we say that's the direction, the magnitude of the friction force, then what sign should I? So minus, okay. Thing that goes in that direction. The x component of the pulling force, right? And so that's going to be the magnitude of F times what? Cosine of whatever our angle was, 25 degrees. Is that it? Okay. And now what about y direction? So we have the gravitational force, so we've got a minus mg, that's the gravitational force. We've got plus what? Plus the normal force, so F n, and now we have what else?
The y component.
The y component of the pulling force, so that's F cosine of what? 65. 65 plus 25 is indeed 90. Now that's sort of a problem because it looks like we've got three unknowns. We've got F, the friction force, we've got the force of the pulling, and the normal force. But is the friction force related to the normal force? Yeah. So we can go friction is equal to mu k times the normal force, and so we can substitute that in here. We have a minus mu k f n plus f cosine of 25 degrees. And now we have two equations, two unknowns. We can solve. The rest is algebra. Questions? Questions? You're allowed to have questions. All right. Okay, so this is really about just being systematic. And we will practice in recitation. In recitation, we'll also look at a somewhat more challenging problem where the momentum is actually changing a little bit, because we can use the same approach for some of these problems. So I want to talk now about what happens if the momentum's actually changing. Is it okay if I erase these? Yeah. So if dp dt is not 0, then in order to solve for an unknown force, we still have dp dt is f net, but if dp dt is non-zero and we want to figure out f net or something that contributes to f net, we need to know dp dt. We need to know the rate of change of momentum of an object. And there are situations in which we can actually figure that out just by observing motion. So let's think about one that's only one dimension, see if we can figure it out in one dimension, and then, so some of you have done a lab already where you hang a mass from a spring and you just pull it down a little bit and then it just oscillates up and down, okay? So that's one of the things you'll do this week if you haven't done lab yet this week. So imagine that you've got a mass hanging from a spring, you pull it down, let it go, it oscillates. And we're going to consider an instant, because we're interested in the rate of change of momentum. So we're going to consider the instant when it's at the bottom. So what is the direction of dp dt when, here's our mass in spring, it's at the bottom. It's actually momentarily at rest, isn't it? So, how do we think about the direction of dp dt at this instant? Got an idea?
Is it like relation with net force? So
Well, dp dt is going to be equal to the net force, but often we don't know the net force on something. So, in fact, so let's just think about what dp dt really means. So remember that dp dt was the limit as delta t goes to 0 of delta p over delta t, since time runs forward in our world anyway, in this classroom. This is a positive number. So the direction of delta p as you make delta t very small is going to be the direction of dp dt. So the way to find the direction of dp dt is to take whatever the momentum is a very short time before the time you're interested in. Okay, so I have to follow my own advice and draw a tangent. Draw a tangent right. So here's some momentum P1 a short time before. Here's some momentum P2 a short time after the time you're interested in. Delta P is just P2 minus P1, and then we think about making that time interval really short. So let's apply that here. So a short time before the time we were interested in, here's our mass and it's going down. So what's the direction at this instant? Down. So a short time after it's reached the bottom, what's the direction of momentum? Up. Now, if we're clever, we'll take these time intervals to be the same, so that the magnitude of the momentum is the same. So how do we get P2 minus P1 again? Tail to tail. So here's P2, here's P1, and now P2 minus P1 goes from the tip of P1, and I won't draw it right on top, so this is delta P. And so if we make these instants closer and closer and closer to the time we're interested in, we're still going to see that delta P is upward. And so in fact the direction of P is also upward. So we're getting dp dt from the motion, because although in this particular case you could infer that the net force was up since it's about to change its direction dramatically, in many cases that's not entirely obvious. And so here we're focusing on just evaluating dp dt without knowing F net. Now, once we've evaluated dp dt, what do we know about that? What can we infer? What can we deduce about the direction of f net at this instant? If we say dp dt is upward at this instant, what do we deduce about f net? It's also upward. Okay, so once we know the direction of dp dt, we can deduce the direction of f net. So here's a more interesting one, where we have an object traveling around, although subtracting collinear vectors is actually always a little mind-bending, but object traveling along an arc, so it's curving, and curving motion is something that we're interested in. And so we want to find the delta p here, the change in momentum of this comet from the time it has momentum p1 to the time it has momentum p2. So which of these red arrows, 1, 2, or 3, is actually delta p? Fingers? 5? 0? Okay, it is 3. That's correct. So we have to take P1 and, well, I guess that's P initial, that's P final, and then delta P goes from P initial to P final. So if we bring these vectors closer and closer together, we'd find that dp dt here is it's kind of like, well, I'm not drawing it very well, kind of like that. And that tells us that the net force also has to be in that direction. Now, does that make sense? There are two characteristics of this trajectory. One is that the momentum is increasing, and one is that it's curving. So that could, in fact, make sense. So in talking about curving motion, we've been writing forces as the sum of two separate parts, one of which is along an x-axis, along a y-axis, and we've been doing the same thing with momentum. But you can always write a vector quantity as a sum of two other vectors that don't have to be along x and y axes. They could be along other directions. And it turns out to be really interesting and useful to think about the components of this vector as the parts of this vector as two pieces. One is a part that's parallel to the momentum. And another part that's perpendicular to the momentum. And why is that useful? Because the component that's along the same line as the momentum, and by parallel I mean it could be parallel, it could be anti-parallel, is associated with a change in speed. And the component that's perpendicular is associated with the change in direction. And those two things can happen independently. So let's think about what it takes to change the direction of something. So suppose we want something to go in a circle. Does that mean its momentum's changing? Absolutely. The direction of its momentum is absolutely changing. So let's see what we have to do to get something to go in a circle. Is this going to work? It is going to work. Yay. Okay, here, stop. So what's happening here is, these are physics professors and physics students making this video. One of them's going to start a bowling ball rolling. And of course, it's going to roll in a straight line, right? And the task circle. So watch what David, who's the guy with the mallet, he's now a physics professor, but he was a grad student at the time, has to do to get the ball to go in a circle, okay? And when he stops hitting it, it goes in a straight line again. So what did he do? What was the direction of the force that he applied at any instant? Altera? Yeah, at every instant it looked like he was applying a force that was actually perpendicular to the motion. So that actually turned it without noticeably speeding it up or slowing it down. So here's this ball at some time, its momentum is like this. He's applying a force this way so that we have an instantaneous impulse in that direction, and that turns the momentum. Now if we do it in finite time steps, we see that we're going to actually change the magnitude of the momentum a little bit, but as delta t gets smaller and smaller and smaller, we get to an instantaneous situation. We see that an instantaneous force perpendicular to momentum just turns the momentum. And so when it was down here going like this, he had to apply a force that way. And when it's here going like this, he has to apply a force that way. So the perpendicular component of a force changes the direction of the momentum. It changes p hat, right? And if he wanted it to go faster, he'd have to apply some force in the direction of the momentum. If he wanted to go slower, part of his force would have to be opposite to the direction of the momentum. So when we're thinking about curving motion, we're going to be thinking about forces that are resolved into a sum of two things: a component of the force perpendicular to the momentum and a component of the force parallel to the momentum. In this case, the component of the force parallel to the momentum was 0, so the magnitude of the momentum didn't change. So how do we calculate parallel and perpendicular components of something? Well, so if we have how how would we resolve F into a component that's parallel to the momentum and a component that's perpendicular to the momentum? Maybe it'll look a little more familiar if I redraw it a different way. Here's momentum. Here's our force. Here's some angle theta. Does that look more familiar? So the parallel component of the force is going to be what? Magnitude of F cosine of theta, right? So what would the perpendicular component be? Come to that in a minute. Now there's a more general way to write this, and it's called a vector dot product. And it's written like this. So now we have one way to combine vectors that we haven't encountered before, which is to take a dot product. And the definition is that the dot product of two vectors, A and B with an angle theta between them, is equal to the magnitude of A times the magnitude of B times the cosine of the angle between the vectors. And it turns out that there's another way to write this, which you can show algebraically is true. And it's actually the x component of A times the x component of B plus the y component of A times the y component of B plus the z component of A times the z component of B. So these are two different ways to evaluate a vector dot product, and depending on whether you know angles or components, now is this vector dot product a vector or a scalar? It's a scalar, isn't it? It ends up being a scalar. So we could write slightly abstractly, the component of a force, the parallel component of F, would be F dot P hat. Okay, so P hat is a unit vector in the direction of P, another thing that some of you need to review. So P hat is a unit vector in the direction of P. P hat is not equal to 1. It's a vector. So a vector can't equal to a scalar. The magnitude of P hat is equal to 1. P hat itself is some vector with x, y, and z components, none of which can be greater than 1. Okay? And if we want to write this as a force, we'd have to write F parallel P hat is a force vector in the direction of P. Okay? So we'll do more with this next time and see if we can apply it to curving motion, and with the goal of figuring out forces causing curving motion. Please pick up your test if you didn't already.